Welcome to the Explainer. All right, we are jumping right into a real mathematical whodunit today. We're talking about a bug. Well, not a standard error code or a computer crash, but a subtle, compounding failure buried deep within the calculus of neural networks. It literally stalled the entire field of artificial intelligence for nearly 2 decades. It's this crazy, fascinating story of how a seemingly perfect mathematical equation hid a fatal flaw that just stopped AI from learning. Let's unpack the mystery of the vanishing gradient.
So, to understand this crime scene, we first have to look at the central mystery that was just driving researchers crazy in the 1990s and early 2000s. Why did making neural networks deeper suddenly cause them to stop learning completely? You see, shallow networks, ones with just 1 or 2 hidden layers, they worked pretty well. They learned basic patterns. But the absolute second researchers tried to stack 5, 10, or 20 layers to grasp truly complex features, the training process would inexplicably just grind to a halt.
Now, the expectation back then was entirely logical. If a shallow network can learn basic shapes, then obviously a deeper network should be able to combine those shapes to recognize faces, objects, and complex concepts, right? Deeper networks should equal smarter AI. But the reality, deeper networks completely flatlined. After just the first few epochs of training, the loss curve would stop improving. The network would effectively just freeze up.
Let's look at the timeline of this deep learning cold case. In 1986, researchers like David Rumelhart, Geoffrey Hinton, and Ronald Williams popularized backpropagation, the algorithm that actually makes deep learning possible. But almost immediately, that freezing problem began. And it wasn't until 1991 that a German graduate student named Sepp Hackreiter handed in his master's thesis at the Technical University of Munich. He mathematically proved exactly why these deep networks were eventually stopping. But because the thesis was written in German, it actually went largely unread for years, and the AI winter just dragged on. Honestly, it wouldn't be until the mid-2010s, with things like ResNet, that the field finally bypassed this bottleneck.
Section 2. The mechanics. How networks learn.
All right, to actually understand Holtreiter's brilliant diagnosis here, we need a quick refresher on how deep networks learn in the first place. Everything relies on backpropagation. You can basically think of it as the method networks use to assign blame for their mistakes. Say a network makes a prediction, like misidentifying a benign skin mark as melanoma. It calculates that error using a loss function. Backpropagation acts like a highly sensitive, multi-dimensional compass. It works strictly backward, moving from the output layer right back to the input layer, calculating exactly how much each internal connection or weight contributed to that wrong prediction.
And the calculus that makes backpropagation possible is the chain rule. Since a neural network is essentially just a massive, nested composite function, finding the gradient or the learning signal for an early layer requires unpacking that function step by step. It goes like this. You measure the error at the end, find the local derivative, which is really just the slope or the rate of change at a specific layer, and then you multiply it by the error passed from the layer ahead of it. Then you pass that new value backward. It's a continuous, unbroken chain of cascading matrix vector multiplication.
Section 3. The culprit. A flawed function. So, if backpropagation and the chain rule are completely mathematically sound, what broke? Well, let me introduce you to the prime suspect in our mathematical mystery, the sigmoid activation function. In the early days of deep learning, this was the absolute go-to activation function. Its whole job is to introduce nonlinearity into the network. It takes any real-valued number and squashes it into a neat, predictable range between 0 and 1, tracing this nice, smooth, S-shaped curve. And hey, it's incredibly useful for outputting probabilities. But inside the hidden layers of a deep network, it turned out to be a silent killer. To understand why it's a killer, we really have to look at its derivative. Remember, backpropagation uses the derivative to find the slope and update those weights. If you actually take the derivative of the sigmoid function, which, by the way, is just the sigmoid output multiplied by 1 minus the sigmoid output, you'll see it forms a bell curve. And the absolute maximum value of that derivative curve occurs when the input is exactly 0. More importantly, that maximum value is always strictly less than or equal to a very specific number.
0.25. This right here, this is our smoking gun. A quarter. Literally, no matter what input you feed into a sigmoid function, the absolute steepest slope it can ever possibly produce during backpropagation is 0.25. Usually it's much smaller than that, especially if the input is pushed toward the edges of that S-curve, where it naturally saturates.
Section 4. The smoking gun, compounding math.
Okay, so the absolutely crucial point here is what happens when you combine the backpropagation chain rule with that maximum derivative limit of 0.25.
because the chain rule requires us to multiply the derivatives as we move backward through the layers. If your maximum derivative is 0.25, just look at what happens. At one layer back, the signal is 0.25. 2 layers back, we multiply 0.25 by 0.25, and that gives us 0.0625. 3 layers back, we're already down to 0.0156. If you have a deep network of, say, 10 layers, well, 0.25 to the 10th power is roughly 0.00000095. You are just multiplying fractions repeatedly. The learning signal is decaying exponentially with every single step backward.
And that math right there gives us the formal definition of our cold case, the vanishing gradient problem. It's a training failure where those gradients shrink so exponentially as they pass backward that by the time they actually reach the early layers, the numbers are basically microscopic. And since the network updates its weights proportional to that gradient, a near-zero gradient means a near-zero weight update.
Because of this compounding math, the gradients of the earlier weights become exponentially smaller than the later weights. Think about what that actually means for an AI trying to learn. The earliest layers are responsible for learning the most foundational representations, stuff like simple edges in an image or basic syntax in a string of text. If that foundation cannot learn, the deeper layers have literally nothing useful to build upon. The entire network just stalls out. It's a completely silent mathematical failure.
Section 5. The resolution. Fixing the fading signal.
So, how did the deep learning community finally bypass this mathematical roadblock and ignite the crazy AI boom we see today? Enter ReLU, the rectified linear unit. Now, I know it sounds super complicated, but it is a shockingly simple mathematical tweak. The rule is literally just this. If the input is less than 0, output 0. If the input is greater than 0, output the exact same number. That's it. It doesn't squash the data like a sigmoid does.
Remember how the sigmoid function maxed out at a gradient of 0.25, guaranteeing that exponential decay? Well, the derivative of ReLU for any positive input is exactly 1.0. When you multiply 1.0 by 1.0 by 1.0 across 10, 20, or even 50 layers in the chain rule, the gradient simply doesn't shrink. The learning signal flows freely backward all the way to the very first layer. This incredibly simple shift in activation functions fundamentally save deep learning.
But to be fair, ReLU wasn't the only fix. Throughout the 2010s, researchers basically built a comprehensive toolkit to stabilize gradient flow. Alongside ReLU and its variants, like GelU, we got smart weight initialization techniques, like He and Xavier initialization, which ensure networks start in a healthy state. We got batch normalization, which recenters data to keep it in a healthy range. And perhaps most famously, residual skip connections, introduced in ResNets back in 2015. Those literally create a mathematical shortcut, allowing gradients to just skip past layers entirely, so the signal is never, ever lost.
Today, the vanishing gradient problem is largely considered solved for standard models. It's safely tucked away as a historical artifact of early AI. But I want to leave you with this thought to ponder. We're pushing the boundaries of AI every single day, right? We're building networks with thousands of layers, processing context windows of millions of words. As we scale to extreme resource-constrained environments or attempt brand new, biologically inspired optimization techniques, will this old mathematical ghost find a new way to haunt our architectures? Thanks for joining me on this explainer. Keep questioning the math and keep learning.